This conference will now be recorded.
Hello everyone, today we will start with reactivity with halogens. That means halogen compounds of group 16 elements. And after this, we will see how the different allotropes of oxygen, one is O2, another one is O3, how we can make them, and what is their physical properties, chemical properties, and also their uses, that is application. Okay, so here when we are talking about halogens of group 16 elements, three types possible: EX6, EX4 and EX2, mainly these three types. And the order of stability of the halides will be like this, that is down the group it will decrease when E is fixed. Suppose if it is E is sulfur, then sulfur fluorine compound, sulfur chlorine compound, that is keeping E fixed. If we consider the stability of the halides, then this should be the stability order. Now, the first type, that is dihalide, EX2, and also there is monohalide, which is most of the time it is remaining in the form of dimer, E2X2. So these dihalides, that is EX2, these are formed by sp3 hybridization. And when it is sp3 hybridization, it is tetrahedral, but there are only two halogen. So other two position, because tetrahedral geometry means 4 coordination, other two coordination side, there must be presence of lone pair. Okay, and when we consider the monohalides, that is the type EX, they mostly remain in the dimeric form. Okay, so these dimeric halides, they can undergo disproportionation. For example, here we have the dimer Ac2Cl2. See, here we have some dimer examples: H2F2, then O2F2, then we have Ac2F2. So these are the examples of some dimer of the monohalides. So from the dimer of the monohalide, now we are getting selenium and selenium Cl4. So in Ac2Cl2, the oxidation state of selenium is +1. But after disproportionation, now it is +4 and 0. That means both oxidation and reduction are going on simultaneously. From +1, when it has lost electron, now it will be converted to +4. And when it has gained electron, now it is converted to 0 oxidation state. So this is reduction, and the first conversion, that is Ac2Cl2 to AcCl4, that is actually oxidation. So this reaction is disproportionation, and for the dimeric halides, there is a tendency for disproportionation. Fine. Tetrahalides, EX4. Among tetrafluorides, that is when X is F, SF4 is gas, then the next element is selenium, selenium fluoride, that is liquid, and TeF4 is solid. So you can understand that when F is fixed and you are moving down, then mass is increasing, because from sulfur to selenium to atomic mass is increasing. So that is why here physical appearance is changing from gaseous state to liquid state to solid state. Now this type, that is EX4, it has specific hybridization, which is sp3d. Now sp3d is basically TBP geometry, and in TBP geometry there will be total 5 positions, but we have only 4 halogen, so there will be one lone pair also. It has trigonal pyramidal structure, that is in short TBP, and one of the equatorial position will there will be the presence of lone pair of electrons. Okay, we will also see the structures in the next slide, but before that we will see what is hexahalides, what are the characteristics. Amongst EX4, hexafluorides, that is when X is F, keeping E fixed, then EF6 are the only stable halides. That is, hexafluorides are the only stable halides. If we compare the other halides, that is suppose ECl6, EBr6, EI6 and EF6. So keeping E fixed, you are just changing the halogen. Okay, so the meaning of the first line is among these four, only the first one is stable halides. Other maybe they can exist, but their stability is not very high. Now the reason is that when E is fixed, then surrounding there are total 6 fluoride. But as we are moving from F to Cl to Br to I, gradually the size is increasing. Now just take the case of EBr6. Now it has to accommodate total 6 bromine atoms surrounding it, but bromine is very large in size. So to accommodate very large atoms, it becomes difficult. Now another thing is also we can think that if the size of E is very high, then why not this one will be stable? Because the central atom, if its size is very large, then it can accommodate the large atoms that like Br minus I minus. So even if E is very large, just take suppose E is tellurium, that is Te, then also this is applicable that hexafluorides will be the only stable halides, because though the size of the central atom E you are increasing, but still this statement that will be applicable. All hexafluorides are gaseous in nature and they are octahedral, so you can understand all the 6 positions. There will be 6 atoms, there is no lone pair. SF6, it is exceptionally stable for steric reason, because sulfur, it can easily accommodate 6 fluoride, and most of the time for EX6 you will see that we give example of SF6. In the next slide we will see the structures of all these different types of halides, and in these 3 different halides the oxidation state will be +6, then +4, and then +2. Because for each halogen you will have charge -1. So if there are 6 halide, that means total positive charge must be +6. Okay, so in this slide is there any doubt? Next we'll see their structures. Structure of halides of group 16. First we have 2 picture. This is dimer of monohalide, that means 2EX equal to E2H2. So here we have example H2Cl2 and O2F2. So this is the fluoride of oxygen and this one is chloride of sulfur. And you can see the structure, you can find some similarity with H2O2 structure, as if you it is having a open books type of structure, because this plane and this plane there is angle of around almost 90 degree. This is also almost 90 degree, and all the bond lengths they are also mentioned. Okay, and this angle is also mentioned. See, this is not exactly 90 degree, it seems as if it is 90 degree, but it is greater than that. Here also it is 1095 degree. Next we will see what about the dihalides. Now for dihalides here we have examples OBr2, OCl2, OF2. Now just consider these 3, because here keeping the central atom oxygen fixed, we are just changing the halides. And the bond angles, because all these are having tetrahedral geometry that we have already seen in the previous slide, where 2 positions there will be 2 lone pair. But the standard angle of tetrahedral geometry is 109 degree. But here you can't see any of this compound that it is having the exact angle, but there is some difference. Okay, but the angle is gradually decreasing when you are moving from bromine to chlorine to fluorine. Now question is very common, that is these 3 compounds will be given and it can be asked that why the bond angle order is such. Now what is the reason behind it? When we are moving from BrClF, basically electronegativity increase. Okay, so Br, it is less electronegative than Cl, less electronegative than fluorine. And if now just focus on the first molecule, that is OBr2, oxygen is more electronegative than bromine, right? In case of second one, again oxygen is more electronegative. But in the last case, oxygen is less electronegative. That means in the last molecule, the electrons of, that is the bond pair electrons between oxygen and fluorine, they will be closer towards fluorine. But in the first two compounds, they will be closer towards oxygen. And in case of second one also, it is just like that. Now if you compare these two, it will be that is electronegativity difference between oxygen and bromine, it is high compared to oxygen and chlorine, because the order is like this: bromine is less electronegative than chlorine, and this is the order. Okay, that means in the second compound also these bond pair electrons will be closer towards oxygen, but not in the last one. So in the last one, this bond pair electron repulsion, that will be minimum. So that is why here the angle is 103 degree. But in case of OBr2, the electron density will be closer towards oxygen. So there will be bond pair repulsion. As a result, the angle will increase. In case of OCl2 also, the angle will be higher than 103, but it is to some extent lower than OBr2. Okay, so this is the explanation behind this type of order of bond angle of that is bond angle of XOX in general liquid. This is another example, ACCl2. Now all these are tetrahedral. Remember, this is the structure. In general, if we write the structure, it will be like this: E carrying two lone pair, and other two positions there will be two halogens. So this is tetrahedral geometry. Next is tetrahalide, that is EX4. It is TBP geometry. Now TBP geometry is, you will have trigonal bipyramidal. That means if it is central atom, there will be X, equatorial position 2x, but there you will have lone pair. So see the structures. This is the first one is TeCl4, TBP geometry. This is the equatorial lone pair. Then again lone pair, TBP geometry for SF4 and TiI4. Here the lone pair is not given. But one question is also you will see frequently, that what is the geometry, that is the shape of this type of molecule. This is the general structure, right? Now if you do not consider the lone pair, that is considering lone pair, it is TBP geometry. But if you do not consider lone pair, without lone pair, the shape is like this, right? And this type of shape is known as seesaw. So seesaw structure is common for tetrahalides like EX4. Up to this point, is there any doubt regarding the structures? And the last type is EX6. Now this is octahedral. So there is no lone pair. All the 6 positions, there will be halogen. Okay, see, mostly we have the smaller halogens, HCl. You will not see here the example considering Br minus or I minus, because when the halogen size is smaller, that is in case of F and Cl, then it will have more stability. Fine. And here oxidation state will be +6. That is, the general configuration is 2s2 ns2np4. But suppose this is ns, this is np. So one electron from ns, one electron from np, it will be transferred to d. So now we will have total 6 unpaired electron, and all these unpaired electron will be used up for bond formation with halide. So suppose if you consider ACCl6, a selenium will use its 6 electron for bond formation with chlorine. Okay. So in this way you can explain how the oxidation state is +6. So should I repeat it once more? Next is oxygen. So oxygen is the first element of group 16 and it is very common element. And why we are giving it so much importance? Because with oxygen, most of the elements in the periodic table, they form compounds and the compounds are called oxide. And oxygen is always written after the any other element because this is always contain the negative charge, because oxygen is the second most electronegative element in the periodic table. Now, when we are talking about preparation, it may be two types, that is industrial method, which is large scale method, another one is laboratory method, that will be small scale method. Now, what about the industrial method? Oxygen we can get from atmosphere, because in atmosphere, if you consider air, in air there is almost 20%, around 20% oxygen. Okay, rest of the percentage is nitrogen and some amount of other gases are also there. So if we can convert air from gaseous state to liquid state, now you will have liquid air. In liquid air also there is presence of oxygen and nitrogen and some other gases. Okay, mainly nitrogen is around 80% and oxygen is 20%, 4:1 ratio, and some other gases. Now this liquid air, just consider it as if it is a liquid, and if you are doing fractional distillation of liquid air, then you can easily separate all the elements. Now liquid air, as it is a mixture of liquid nitrogen and liquid oxygen mostly, I'm not saying that these two are the only gases present. Some other gases are also present, but these two are mostly prevalent. Their boiling points are minus 196 degrees centigrade, and for oxygen, the boiling point is comparatively high. Okay, this is minus. There is a minus sign. That means this value is lower than this. So it means that oxygen will be first. We will get oxygen because it will be easily. Its boiling point is low. So first we will get nitrogen during distillation, then we will get oxygen. So this is basically more volatile, so it will boil up fast and oxygen will be remaining in the content. Here we have taken air. Now when you are giving very high pressure, it will be converted to liquid air. Okay, now this liquid air, that is called compressed air. Now what we are doing fractional distillation, and in this fractional distillation, nitrogen gas, that will be removed because its boiling point is lesser, and liquid oxygen will be there present, because now when nitrogen is already removed, there will be only liquid oxygen remaining. So in this way we can get oxygen industrial. And this is the structure. See, this is diatomic, and oxygen, there are total 6 valence electron. It is using 2 electron for bond formation with other oxygen atom, and rest of the 4 electrons are present as lone. Similarly, the other oxygen atom also, it is using 2 electron for bond formation, and these two are the lone. But this is industrial method. There are some other methods. From metal oxide, thermal decomposition of oxides of metal, but not just any metal we can't take. That metals which are low in the electrochemical series. That means low means where the that is, if we consider the reduction potential value, here the reduction potential values are less negative. That means towards more positive values. More positive value means their tendency for reduction, that will be very low. So these metals, it will be mostly there will be tendency to get reduced. Okay. Here we have taken silver oxide, manganese oxide, mercury oxide, and lead oxide. Here from Ag2O, see, in Ag2O the oxidation state of Ag is +1, but now it is 0. And MnO2 it is +4. Now it is Mn3O4. Okay, so and oxygen is also we are getting. Total negative charge is 4 into -2, that means -8. That means +8 charge that will be distributed between 3 Mn. And Pb3O4, it is converted to PbO and O2 HgO. That is also here the reaction is, you can find some similarity with the first reaction. So all these are basically metal oxides, but you cannot take any metal, only the metals that are low in the electrochemical series. Low in the electrochemical series means the less electropositive metals. Fine. Thermal decomposition of oxygen rich salt. So for oxygen rich salt, what salts we have taken here? Potassium nitrate, potassium permanganate, potassium chloride. Potassium nitrate decomposed, so you have to apply heat. Basically these equations are also, there should be this sign. When you are heating it, KNO3, it is liberating oxygen and itself is converted to KNO2. Similarly, KMNO4, when it is heated, now it is converted to K2MnO4. So KMnO4, potassium permanganate, this is potassium manganate, and MnO2 and O2. So O2 is produced. That is our main concern. And potassium chloride, in presence of catalyst manganese dioxide, now it is converted to KCl and O2. So all the oxygen atoms are removed. And one more method from hydrogen peroxide. Hydrogen peroxide is H2O2. Again, we are using the same catalyst and it is decomposed to water and oxygen. So all these chemical methods can also be used for production of oxygen when it is not industrial method. Okay. Is there any doubt in the preparation method of oxygen gas? Now, physical properties. Oxygen gas is odorless, colorless, tasteless. It is heavier than air, which is clear from this density value, 1.429 gram per liter. Water solubility is there, but it is not very high. But remember, to support aquatic life, because for aquatic life, there is requirement of oxygen. So there must be some solubility of oxygen in water, otherwise aquatic life cannot sustain. But they can sustain with this amount of solubility. That is, whatever is the solubility, though it is very slight, but still it is sufficient to support aquatic life. Melting point, see, this is very low value. It is in terms of Kelvin, but if you convert it to degree centigrade, it will be negative, right? Boiling point, 90 Kelvin. It can remain in all the three forms, and all these three forms are very common to us, right? Solid, that is ice, normal, I'm saying solid oxygen, liquid oxygen, and gaseous oxygen. So gaseous oxygen that we mostly see, but solid and liquid oxygen, that is also possible. And it depends on what temperature and pressure you are applying. So under normal condition, it is gaseous, but you can, depending on temperature, pressure, you can also convert it to solid oxygen and liquid oxygen. Now, solid oxygen and liquid oxygen, there is a specific color. So when it is liquid and solid, there is pale blue appearance. 3 stable isotopes of oxygens are there, 16, 17, 18. So mass number is different. Isotope means when atomic number is same, but because of difference in neutron number, mass number will also be different, because mass number is summation of N and P. P is fixed, but N is changing. So liquid and solid oxygen, if we see, this is the picture. This is liquid, this is solid. Molecular oxygen, that is the diatomic form O2, not oxygen atom. We are saying molecular oxygen, that means O2. It is unique in being paramagnetic. Now this is very important. You will get frequent question regarding this nature of oxygen, that it is paramagnetic. Now, despite having even number of electrons. Now, why we are saying even number of electrons? Because two oxygen atom, each oxygen atom valence electron 6 and 6. So 6 and 6, if you add, it will be even number of electrons. Then why it is paramagnetic? Paramagnetic means presence of unpaired electron, but there are even number of electrons. So to explain this observation, basically you have to first draw the molecular orbital diagram, which is this one. Now see, here we have oxygen atom both side, two oxygen atom, each carrying 6 valence electron. See, here 6 valence electrons by black dots are given. Now it is 2s2, and 2p4. So in 2s2 there are 2 electron, 2 electron. In sigma 2s there will be one paired electron. Sigma star 2s, that is anti-bonding, there will be also one electron pair. Now when you are moving to 2p, 4 electron, 4 electron. Total number of electrons will be 8. Now how we are arranging the electron? For that you have to know what is the different energy level. So the first is sigma 2p. That is when 2p orbital are forming sigma bond by head-on overlap. Then we have 2 pi. Now pi bond means this type of sidewise overlap. And here we have pi 2px and pi 2py. Because all the p orbitals are not used for pi bond formation. It is only 2p orbital that are used. And next we will have antibonding. So see, pi 2px star, pi 2py star, and sigma 2p star. Now if x and y axis is there is pi bond, that means sigma bond will be formed in the z axis. Because if it is z axis where head-on overlap is there, then sidewise overlap means it must be perpendicular to this axis, and perpendicular to z is y and x axis. Okay, but come to the actual point. The point is here. Now if we arrange 8 electrons, this is one pair. In pi there will be total that is, it will occupy total 2 electron pair. Now you have only 2 electron pair left, but according to Hund's rule you have to place 2 electron 1 1. I mean to say, you cannot write it like this. This is not correct. First you have to place 1 1 electron, then there will be pairing, but you do not have any more electron, so pairing is not possible. So you have here 2 unpaired electrons, and these 2 unpaired electrons, that is the actual reason why oxygen is paramagnetic. Now this MOT representation, MO representation, that you can also do in this way. Sigma 2s2, that means this one, 2s star 2, then sigma 2p2, pi 2p4, that is this one, and pi 2p star 2. So here we have actually one unpaired electron, and for that it is paramagnetic. And bond order also we can calculate, that is total number of bonding electrons minus total number of anti-bonding electrons divided by 2. So this 2 minus 2, it is for this one, these two. Then 2 plus 4, that means 2, 4 in bonding, and minus 2, which is for this antibonding. So after calculation you are getting 2, and bond order is nothing but the total number of bonds. So as you are getting bond order 2, that means there are 2 bonds present between oxygen, 2 oxygen atoms. So in this way you can get so many information for the molecular orbital diagram. What is the bond order, why it is paramagnetic, okay, all these informations. So is there any doubt in this slide? Now we will see its chemical properties. Now oxides are very large and important class of chemical compounds, because oxygen is such an element which is very reactive, right? Now that is the reason almost all the elements in the whole periodic table, they form compound with oxygen. Okay, so if I am considering E, and that is any element in the periodic table, and it is forming compound with oxygen. Now oxygen is the second most electronegative. First is fluorine, then oxygen. Now if that is the case, then except fluorine, all the other elements in the periodic table, they will always be less electronegative than oxygen. That means it will carry positive charge, it will carry negative charge, and that is the reason we call it as oxide, because the negative part, that is written, that is mentioned later. For example, if we say nitrogen oxide, okay, you do not say that it is oxygen nitrogen. Okay, what we say nitrogen oxide, that means nitrogen will be more towards more positive because oxygen is more electronegative, and we will end the name with oxide. So that is why oxide is the general term. Just like oxide If you have S-2, it will be sulfide like this. So they are very important and large and important class of chemical compounds in which oxygen is combined with another element E. Now, with the exception of lighter inert gases, now not all the inert gases, only we are talking about lighter inert gases. Helium, neon, argon, krypton, then xenon, then radon. So xenon, radon, these two are heavier because down the group you are getting this. So except these lighter inert gases, oxygen can form at least one binary oxide with each of E. Okay, except these elements. Now, as it is, they are inert gases, so obviously they will not take part in reaction. They are reluctant to take part in reaction. So that is why they are not forming compounds with oxygen. But if you move further krypton, that is xenon, radon, now what happens? Reactivity gradually increases down the group because outermost electrons, they are now far from the nucleus, so they can easily take part in reaction. Ionization energy is also very low, so that is why the heavier inert gases, they are comparatively more reactive compared to the lighter inert gas, so they can form compound with oxygen. And you have probably heard about xenon oxide, okay, like this. So now we will see the actual reactions with some elements such as H block elements, that is sodium, potassium. Okay, there is combination of oxygen, and this is very reactive. That is, the H block elements are very reactive. The most electropositive metals in the whole periodic table. They are at the leftmost side of the periodic table, right? Now oxygen is already reactive. Now these metals are also reactive, so that is why the reaction will happen very easily and it will take place at room temperature. You don't have to provide any external temperature. Oxygen normally doesn't react with acid or bases. Okay, if you simply mix it, there it is not that there will be some reaction. Its combination with other elements is strongly exothermic because we know that this is very reactive. But that does not mean that you don't have to provide any temperature, because when it is exothermic, what we know according to Lee-Chatelier principle, that if you provide more energy, now the reaction will not be spontaneous, because exothermic means energy is released, del H is negative. Now when del H is negative, normally we know that low temperature is preferred, but still to initiate the reaction, that is to overcome the activation energy, you have to provide some amount of heating, because you have to break this double bond between two oxygen atoms, then only it can take part in reaction. And this bond energy value, see, this is very high, 493.4 kilojoule per mole. So you have to provide temperature to break this bond. So to initiate the reaction, though it is exothermic, you have to provide some temperature. It combines with many metals and non-metals. So this side we have metal, and right hand side you have non-metal. Now, when we are saying metal, you can see different types of metal. Sodium, which is from S block, iron from D block, aluminium from P block, and in all cases you are getting oxide of the metal. And we have some non-metals, carbon, sulfur, hydrogen. Okay, all these compounds are very common, it is known to us. Good oxidant and hence support combustion. So if you have taken any fuel, mostly it is hydrocarbon, that is compound of carbon and hydrogen, and you will always get that production of CO2 and H2 is there. So for example, if you have taken methane gas and if you are doing combustion reaction is basically reaction with oxygen, and remember it is always exothermic in nature. Now there is carbon and hydrogen both, though it is not balanced. CO2 4 hydrogen, that means it will be 2H2. And what is the total number of oxygen? 2 here, that means total 4 oxygen. So in this way you can balance it. So remember, in combustion products are always carbon dioxide and water, and huge amount of energy is also liberated. In some cases you have to add some catalyst, that is simply adding it is not enough. For example, reaction between ammonia and oxygen. In this case you have to use platinum catalyst, and the product is not single product. Products are nitric oxide and water. Then reaction with sulfur dioxide. Now sulfur, it is that is SO2 is oxide of sulfur, but now you are getting another oxide of sulfur, which is SO3. So here it is acting as oxidizing agent, obviously oxygen, so it will be oxidizing agent. Oxidation state, if you see, it is +4 before reaction, +6 after reaction. So it is obviously loss of electron, and it is oxidized. Sulfur is oxidized. But what catalyst we have taken? B2O5, vanadium pentoxide. And reaction with HCl, here we are providing this catalyst, copper chloride, and we are getting chlorine. So from -1 charge in HCl, it is chloride carrying -1 charge. Now it is having 0. That means loss of electron. Okay. So these are the examples of some chemical reactions. Any doubt? Now we know water oxide, but we have to next know what is different types and nature of oxide. Now I have mentioned it several times that when it is metallic oxide, it is mostly basic oxide, mostly, not always. When it is non-metallic oxide, it is acidic oxide. Again, it is mostly, not always. Now you can understand why it is so. Because when it is metallic oxide, it may be basic or it may be amphoteric. Now amphoteric means having characteristic in between basic and acid. It can react both with base and acid. And basic oxide means it will react with acid only. Acidic oxide means it will react with bases only. Now when it will, how you will understand that when metallic oxide will be towards basic side or amphoteric side? Now that is also easy to understand. Here you can see from the examples, sodium and calcium. Now these elements are these metals are from S block, and S block metals are very reactive. So when the metal is highly electropositive, you will be getting the idea that it will be now basic oxide. But if the metals, these are also metals, but it is D block and P block, and obviously less electropositive than S block metals. So this will form now amphoteric oxide. And now come to the non-metallic side, acidic oxide, neutral oxide. So here acidic oxide example we have C, carbon and sulfur, and in the neutral oxide example we have hydrogen and carbon. Now see here, if you are thinking that carbon is present as example in both side, acidic and also neutral. So how you will understand? So carbon is non-metal, that is okay, but here oxidation state of carbon is different. Here it is +2 in CO, but here it is +4. So when the oxidation state is high, element is same, in both cases it is carbon, but in one case oxidation state is high, another one is oxidation state low. So high oxidation state means it will be now acidic in nature. Okay, and higher is the non-metallic character, higher will be the tendency to move towards acidic oxide. Okay, but you also have to be very careful about the oxidation state, because same element, that is carbon, it can form acidic oxide and also it can form neutral oxide. Neutral oxide and amphoteric oxide, what is the difference? Amphoteric oxide, it can react with both acid and base, but neutral oxide, there will be no reaction. Some more examples, and also how you will be, that is some basic definition. Acidic oxide, these are the examples. Reacts with alkalis to form salt. Basic oxide, these are the examples. Now see, sodium, calcium, potassium, Mg, copper. Reacts with acid to form salt. Then amphoteric reacts with both acid and alkalis. And neutral do not react with both acid and alkali. Another example, C. This is also nitrogen oxide. This is also oxides of nitrogen. But what is the difference? Here oxidation state of nitrogen is +1. But here it is +4 and +2. Again the same thing that I have said in this CO2 and CO case. That is higher oxidation state, same element but higher oxidation state, that means it will be towards acidic side. But one thing, okay, first see this example as Al2O3 amphoteric, that means it will react with acid alkali both. So first there is example of reaction with NaOH. It is producing salt, sodium metaaluminate, and it is producing water also. And when it is reacting with acid, now it is forming aluminum chloride and 3 water. Fine. So sodium metaaluminate, that's how you will be able to understand oxidation state. If you just remove the sodium, now charge over AlO2 is -1. Now 2 oxygen atom means total negative charge -4. So the oxidation state of aluminium will be +3. So here also it is +3, here also +3. In both cases +3, but it is having in different compound. That is AlO2 minus, that is in the anionic part, but here it is in the cationic part. Okay. Now we will see some exception. It is actually not exception. There are some explanation behind it. That some metal oxides are acidic at higher oxidation state. As I have said, see this nitrogen oxide, in both cases there is example of nitrogen oxide. But what is the difference? Here oxidation state is low, but here it is high. So similar explanation now you can also apply. These oxides, though they are metallic oxides, so what you will expect? You will expect either they will be basic or amphoteric, because according to this flowchart, that should be the case. But what is happening here? Oxidation state, if we see Mn2O7, what is the oxidation state of manganese? It is +7, because 7 oxygen, each oxygen is carrying -2. That means -2 into 7, total negative charge -14. And you have 2 manganese atom. That means total positive charge is 14. So each manganese will carry +7 charge. Okay. So in this way you can find out oxidation state. Similarly for chromium it is +6, for vanadium it is +5. So oxidation states are very high. Manganese can have different types of oxidation state. It may be +2, +4, +7, but +7 is the highest oxidation state. So when it will reach highest oxidation state, same is also for chromium and vanadium, +6, +5, they are highest oxidation state. So as the oxidation state is very high, so that is the reason they are acting as acidic oxide. Fine. Any doubt? Can I move to next slide? Application of oxygen. It is one of the essential components of survival of living organism that you all know. Used in oxygen cylinder that are used in hospital and for mountaineering. Then oxyacetylene, which is basically the mixture of oxygen and acetylene gas. Acetylene gas is C2H2. Oxyacetylene flame is used for cutting and welding metals. So here what happens, acetylene is basically hydrocarbon because it is C2H2. So hydrocarbon in presence of oxygen, there will be reaction and huge amount of energy will be released. So this energy will be used for cutting and welding metals. Rocket fuel, there is use of oxygen in liquid form. Then laser cutting, combustion process, example we have already seen. In water treatment process for purifying wastewater and treating sewage. Now here we have a problem. Which of the following gas mixture is used by the divers inside the sea? So here if we look at the options, oxygen is fixed, but other gas is changing. These three are inert gases. Okay. Nitrogen. Now nitrogen in air, if we consider, there is already presence of oxygen and nitrogen. So if we take air in the cylinder, that is now where nitrogen is present. That is, if you take oxygen, it will mostly combined with nitrogen because naturally oxygen and nitrogen are mixed in air. Now what will be the problem? Nitrogen under high pressure, because when we are talking about diving under deep water, there will be very high pressure, and because of this high pressure, solubility of nitrogen gas in blood will increase, and as a result, and this is not very good for the divers, because now there will be nitrogen narcosis, which is a specific problem that will arise, some symptoms are there. So that is why, to avoid this, what we do, we have to mix a gas which should be having low solubility in the blood. Okay, and though all these three are inert gases, but helium will have the most low solubility. Okay, so because of its low solubility, that is, it means helium, as compared to nitrogen in blood, a mixture of oxygen and helium is used in diving apparatus, which is used by deep sea divers. But if we take normal water where oxygen nitrogen ratio is almost 1:4, then nitrogen narcosis will be there, and there will be some unconsciousness symptoms, which is not good, and that is why mixture of O2 and 2, it is never used. But which mixture is used? It is oxygen and helium. Fine. Now another allotrope of oxygen is ozone. So oxygen exists in two allotropic forms. Allotrope means different physical forms, and namely dioxygen and ozone. You can also call it trioxygen. Just we say di, so it will be tri, because now we have three oxygen. Natural occurrence, if we consider, there is negligible amount of ozone gas at sea level. But why it is negligible amount? Because its stability is not very high, it is very reactive, so that is why it cannot exist as O3. Very low amount is present. At a height of about 20 km from Earth atmosphere, it is formed from atmospheric oxygen, because at this height, in presence of sunlight, that is, we can say H nu, atmospheric oxygen that will be converted to O3. Now this process is not very spontaneous process, because O2 is very stable, O3 is very unstable. So this conversion is not very, it will not take place very easily. But as at this height, there is presence of some special radiation. So in presence of that high energy, this conversion will be possible. There is an ozone layer at this height, 20 km. So if we consider Earth, there is an ozone layer at 20 km. Now this layer, it helps to protect inhabitants from intense UV radiation. So the UV radiation that are coming towards Earth, that will be absorbed in this ozone layer, and as a result, it will not reach to us directly. So in this way, we can get rid of it. So it is protecting us. If the concentration rises above 100 parts per million, then it is not good for us. There will be problem in breathing, ultimately headache and nausea. So in low concentration it is fine, but high concentration, though that is hardly the possibility is there, because see here we have very negligible amount of ozone. But if it is crossing this limit, then there will be some problem. Physical properties. Now ozone, as you can see, it is unstable deep blue diamagnetic gas with fishy smell. So there is specific smell. In case of O2, you have not seen any smell, and it is also having some color, unlike oxygen, and it is diamagnetic. See, there are so many differences. So they are allotropes. There are difference in physical properties. Oxygen, there is no color, but it is deep blue. Oxygen is paramagnetic, but now it is diamagnetic. Oxygen, there is no specific smell, but now you have some specific smell. Density with compared to oxygen, it is very high. Melting point, boiling point mentioned, both are obviously towards negative side, because under normal condition it is gaseous. And you can see here two resonance structures. Both the resonance structures are equivalent. But if you are numbering the oxygen, suppose 1, 2, 3, now we will be able to understand, because in the first structure, number 1 oxygen is neutral, but in the second structure, number 3 oxygen is neutral. Similarly, 2 oxygen is carrying positive charge. This is also same. But here 3 oxygen is carrying negative charge, here it is neutral. So there is some difference, but it is equivalent resonance structures. How you can get it? If this negative charge is forming bond here, now oxygen 1 will carry negative charge. its intense blue color is because of absorption of red light. So the complementary color we are seeing. Now red light absorption wavelength range is this 200 to 310, but color is because of this reason. Remember, this may be an important question. Again, water solubility is very low, but if you take non-polar solvent, that is organic solvents like CCl4, fluorocarbon, that is compounds of carbon and fluorine, then solubility is better. If it is below melting point means obviously now it will be in solid form. Now it is violet black, but it is so intense color as if its appearance is like it is almost black. If it is below BP, now it will be blue liquid, that you can see here. Blue liquid, that means liquid ozone. Okay. So there are so many differences if we compare physical properties of O2 and O3, right? Preparation of this gas. Now its preparation is completely different. See, we are using some electrical energy to make this compound. Okay, and there is a specific instrument we are using which is known as Siemens ozonizer. In this instrument, what we are doing, you can see here horizontal U-tube type of shape, U-shaped tube. Now we are passing oxygen here. There is a presence of tin foil both inner surface and outer surface, and there is a specific role for this tin foil. It is used to coat inner side of the inner tube, outer side of the outer tube, and these tin coatings are now connected to the terminals of an induction coil. See, this is connected, outer surface, inner surface, that is also connected. And as if this tin coating that is there, it is as if acting as electrode, metal electrode. Now it is producing high voltage current. This low current of high voltage current, that is fine. Now what we are doing, a slow current of pure and dry oxygen, that is oxygen gas is flowing through this terminal. It is passed through the annular space, and when this oxygen, it is subjecting to silent electrical discharge. Now this word is very important, silent. Okay, we will come to that point. Silent electrical discharge. The electrical discharge must be silenced. There should not be any production of sound. We are getting ozonized oxygen. Now what is ozonized oxygen? It is nothing but mixture of O3 and O2. But the amount of O3 is 10 to 15%. That means from O2 you will get O3, but its conversion is very poor because mostly it will try to remain towards oxygen side, or because oxygen is more stable. So ozonized oxygen, this mixture you will get. That means you are not getting pure ozone. You are getting ozone, but it is still mixed with unreacted ozone. Now how to get finally pure ozone from it? Pure ozone can be get if we are doing fractional distillation. Okay, so pure O3 is obtained as a pale blue gas by the fractional distillation of liquefied ozonized oxygen, because there is difference between their boiling points. Okay, so that is why fractional distillation is possible. So this is the reaction, oxygen first converted to atomic oxygen. Now this atomic oxygen, which is actually also very reactive, this oxygen will combine with O2 and finally we will get ozone. But remember, in this reaction some unreacted starting material, that is O2, will also be mixed. So finally you have to, if you want to get pure ozone, you have to do fractional distillation. Now the important question is why it is silent, that we will see. If we look at this energy profile diagram, this is oxygen, this is ozone. Okay, now from the energy you can understand that energy of oxygen is lower than the energy of ozone. That means this reaction, you are getting product from reactant. Product is having higher energy. That means this is endothermic reaction. And here, if we take the difference between product and reactant, this difference is delta H. which is at 298 Kelvin, 142 kilojoule per mole. This amount of energy is absorbed, so this is endothermic reaction. Now basically here you are making some unstable molecule starting from some stable molecule. So this conversion is not very, it will be very poor. Mostly the reverse reaction, that is from O3 to O2, that will be more spontaneous, right? That means when you are trying to prepare O3 from O2, it is difficult process. And in this process, as it is endothermic, you have to provide energy. Now this energy we are providing in terms of electrical energy, not heat. Okay. So that you have already seen in the last slide. Now in this case, if there is any production of sound, some amount of energy will be lost. But we cannot lose energy because their energy is very important. We are providing energy because the process is not spontaneous. But if there is any production of sound, that will be energy will be wasted. That is why silent discharge is important. So decomposition of O3 into O2, there is liberation of heat. That means when you are considering the opposite reaction, reverse reaction, it is negative because O2 to O3, that is endothermic, del H positive, so this is negative. And there is also increase in entropy. Why? Because if we write the balanced equation, it is 3O2 to 2O3. So from 3 molecules, you are getting 2. Okay. But if it is reverse reaction, now from 2O3, you are getting 3 molecules. That means entropy is positive. Now when entropy is positive, from this reaction, del G equal to del H minus T del S. Del H is already negative and del S is positive. That means del G will be highly negative. So it is highly spontaneous. That is the reverse reaction O3 to O2, that is highly spontaneous. So that is the reason high concentration of ozone, it will be dangerously explosive because it will always try to convert to O2, another allotropic form. So some precautions we have to take to increase the yield of ozone when you are trying to make ozone from starting from O2. Only pure and dry oxygen should be used. Ozonizer should be perfectly dry. There should not be any moisture. Temperature is low because the energy we are providing in terms of electrical energy, not heat. Since the formation of O3 from O2, it is endothermic energy requiring process. So silent electrical discharge is required in its preparation so that decomposition is not there. That means the O3 that you are making, that should not be further decomposed to O2. That is not desired. So that is mentioned here. Okay. So these are the reasons why silent electrical discharge is important, and these are the precautions that we have to take because this process is not very facile process. It is very difficult process. So that is why we have to take these precautions. Now we will end here. Some examples of chemical properties of O3 that we will discuss in the next class. So regarding all the slides in the whole class, if you have any doubt, please mention. So there is no doubt. So we are ending the session here. Thank you for listening.